Hello everyone, I'm Joe. Welcome to my channel. Today we will talk about the Boolean theorems and how to use them to simplify some complicated Boolean expressions. Just like in the math, we have some theorems and laws to teach you how to figure out the result for a given Boolean expression and how to simplify them. So let's start with single variable problems. First is the operation with 0 and 1s. So let's check the first one. So x is a Boolean variable. So if we have a variable to all with the 0, it should equal to itself. So let's try that because we know x can either be 0 or 1, right? If it's 0, 0 or 0 should be 0. If it's 1, 1 or 0 should be 1. So this is true. And if we have a variable to all 1, always equal to 1, right? Because we know that for all function, if one input is 1, the output should be 1. Okay. Similarly, for add function, a variable add 1 always equal itself. A variable add 0 always be 0. Then the second law is called idempotent law. So basically, a variable or itself should be itself. And a variable and itself should equal to itself too. And you can always put some value to try it out. So 0 or 0 equal to 0, 1 or 1 equal to 1, right? 0 and 0 you get a 0, 1 and 1 you get 1. So this is always true. And then the involution laws. Involution laws basically says if you take the opposite of the variable, you get itself. So not the not, you get the original variable. Again, you can take the value, so x prime and prime, so we get 1 prime, which is 0 itself. For 1 prime, you get 0 inside the parentheses, and prime, you get 1, which is equal to itself. So this is true. The last one, laws of complementarity. Basically, it states that if you have a variable to all its complement, you get 1. Or if you have a variable to and its complement, you get 0. So complement here, I mean same as not. So complement also means the opposite of the original value. Okay, now let's look at multivariable theorems. And for the first two, they are just the same as what we learned in math class. Right? The commutative law basically says you can switch the place of the variables without changing the result. Associative law states that you can find out the result for using any sequence in the expression without changing the result. Right? Then we have the distributive laws. The first format, so x and the result of y or z should equal to x and y or x and z. This is also looks familiar to what we learned in math, so I won't talk too much about it. But if you check this second one, it can be a little different. So let's try to verify this. So let's try to prove this theorem here. So let's start from the right. So I have x or y, x and x or z. So if we open the parentheses just like what we did in math, so we got x and x, or x and z, or x and y, or y and z. So from here we know this is from, if we check the previous slide, we can find this should equal to x itself, right? Any variable and itself equal to itself. So we get x or x and z, or x and y, or y and z. Okay. Then if we combine the first two terms, we can get x, 1 or z, or xy or yz. And because 1 or z always equal to 1, and x and 1 equal to x, so we get x or xy or yz. Again, combine the first two terms here, so we get x and 1 or y or yz. So 1 or y always equal to 1, and x and 1 equal to x. So finally we get x or yz. So this theorem is also true. Next is the most important laws, which is called De Morgan's laws. So basically it says that if we have a Boolean expression like in this format, x or y takes prime, takes the prime of the result, that should equal to x prime and y prime. Basically, this allows us to convert an OR function or NOR function into an add function. And similarly, if we have an add function, we can use De Morgan's law to convert it back to an OR function. Basically, this is what it says. And when you apply this law, just be careful, don't make those common mistakes. Okay, you must using these two, not these two. Okay. And what's the real application for De Morgan's theorem? As I said, it is very useful. For example, we have an add function y equal to a and b. We know that we can realize this function using an add gate, right? But if we apply the De Morgan theorem and make some change to it, what we can get is, first, let's first rewrite a and b into the format like a and b prime. It's prime, right? If we take lot 2 times, we basically didn't change anything. So not the lot equal to itself. Now, inside the bracket, we can apply De Morgan's law, which equal to, if we follow this one here, it's equal to a prime or b prime. So what did you find? If we realize this function using the logic gate, right, we need an OR gate, and the OR gate will take the input A, but we need inverted, and also B, we also need inverted. Then we need to add the third NOT gate here. So what you have found is that these two circuits actually equivalent to each other, and sometimes we can simplify the NOT gate just using one bubble. So this also can be drawn like something like that. So these bubbles represent the lot function there. Okay. So you can see that instead of using an add gate to realize the add function, we can also using a NOR gate and some NOT gate to do the same job. So that's very useful in real design. Okay. And similarly for A or B, we can do similar things. So first, rewrite this expression to a format like this: A or B prime and prime. So this equal to if we apply the De Morgan theorem, we get x prime y prime prime. Again, we used to have an all function. So let me separate this. A and B, and output is y. Now we can equivalent this to use a NAND gate first, but with two NOT gate at the input. Sorry, I should put A, B, not X, Y. So these two are equivalent. Let's try it again with another example. So let's find the De Morgan's equivalent form of the 3-input NAND gate. So for the NAND gate, here the function f equal to x and y and z, but we need to take the NOT. So that's the 3-input NAND function, right? And if we take using the De Morgan theorem, we can rewrite this as x prime or y prime or z prime. Okay. So which means this gate is equivalent to a different gate like this. With bubbles in front. So x, y, and z, f. So this is the De Morgan equivalent. Before we talk about the rest of the laws and the theorems, let's first talk about the concept of duality. So for each Boolean algebraic expression, it has a dual expression. A dual expression can be obtained by interchanging the AND and the OR operators and replacing the ones by zeros, and replacing the zeros by ones. One thing you need to be aware is that the dual expression is not equal to it's not equal to the original function. Okay, there are two different functions, but we introduce this because this simplify our work. Okay, so to give you some example, so x and 1 equal to x, we know this is true, right? We already know it's true. Then we can find its dual. The dual is obtained by interchange AND and OR. So we have AND function, just change to OR function here. And also we replace the ones by 0. We got some ones here, which is replaces with 0 and keep the x. And the right, nothing gonna change, keep it as x. So we got the dual for x and 1 is the x or 0. Okay, so if the original function is a true function, then its dual function is also true. So that's why we introduce the dual, which means if we can prove one expression is true, then its dual expression should also be true automatically. Okay, so that's why we do this. To give you an example, let's see how to find the dual. For A, the original function is x, or y, and z. To find the dual, first we change the OR function to AND, and the AND to OR, because we have another add function, so we also need to change that to OR function. But you don't change the sequence of the operation, so which means I need to put the parentheses here to mean that y or z should be find out first. Then x just right here. So the dual expression for x or y and z should equal to x and y or z. Similarly for b, we got two OR function and one AND function. First, change the OR function to AND. then change the and to O. There's no 1 and 0 there, so we don't have to change it. Okay. So this is the dual. Again, this dual function is not necessarily to equal to the original function. Sometimes they may equal, but most time they don't. Now let's look at the simplification theorem and their duals. The first one is called the uniting theorem. Okay, so we only need to prove one of them, then the other one is automatically true because it's the dual of the original one, right? So let's try to prove the left one here, 2-15, the law 2-15. This is from the textbook, so I have the number there. So let's try to prove it. Okay, so starting from the left, x and the y, or x and the y prime. If we apply the theorem we talked before, which is 2-11, which is the distributive law, so this can be put as x and the y or y prime. Then we apply the law 2-8, which says that y or y prime should equal to 1. Finally, apply 2-4d. D means dual. This is equal to x. So it's proved. Then we don't have to prove this because it's a dual. So it's also true. Next theorem is called absorption. Again, let's try to verify the left one. So proof. Yeah, when we look at this, because x can be written as x and 1, right? This is from 2-4d. Okay, so the left side of this expression become x and 1 or x and y. So again, we can use the distributive law, which is 2-11, to put it at x and 1 or y. Now, if we apply 2-5, 1 or y should equal to 1. And using 2-4d again, we get x. So it's true. And the right one is also true. So 2-16d is also true. Next theorem is called elimination. To prove this one, it's a little bit more tricky. So what we do is first we need to apply the theorem we learned before, which is the dual of 2-11 for the distributive theorem. Okay. Then what we have is for the expression in this format, this is equal to x or y and x or x prime. Yeah, if you can tell why is this, go back to the page, the previous page, to check this one. And this we just write down. And the second term, x or x prime or lot x, we know that it's always equal to 1, right? So finally we got x or y. This is actually 2-4d. Oh, sorry, this is not 2-4d. This is 2-8. Yeah, it says a variable or its complement equal to 1. Okay, then this one is 2-4d. So a variable and 1 always equal to itself. The last theorem is called consensus, and the proof for this is kind of harder than the previous ones, but let's try it. Again, we start from the left side of the first one. We don't have to verify the second one, as long as we can verify the first, the original one. So to prove this, we need to first do this. So x and y, or x prime z, or y and z. Here we change it a little bit, so we put this as 1 and y and z, because any variable add 1 equal to itself. Okay, so this is using 2,4-D. Then next step, we write one as x or x prime. This is according to 2-8. Then let's open the parentheses. So we got x, y, z, or x prime, y, z. This is from the law of distribution, right? Or distributive theorem, which is 2-11. Okay. Then if we combine the first term and the third term, we get x and y, 1 or z. And if we combine the second term and the fourth term, we get x prime z, 1 or y. Okay. Again, this is using the distributive theorem. So 2-11. Basically, we also apply the 2,4-D here, because we write x and y to x and y and 1, x prime z to x prime z and 1. Okay. Then because 1 or z equal to 1 and 1 or y equal to 1, so we get this. Again, here we use two theorem here. 2-5 and 2-4-D. Then it's proved. Okay, so on this page, I put all the theorems and laws we have learned here as a summary, and we will have a final practice problem to see how to use them. Before we go ahead and do the simplification, I want to clarify that the reason why we need to simplify the Boolean expressions. Because you know that the Boolean expressions really can determine how we wire up our physical circuit. So if we have a simpler Boolean expression, which means our circuit, the logic circuit, will be simpler, right? And the simpler logic circuit, most time it means we have no cost, high performance, and high speed. So that's why simplification is actually very, very critical. So now let's see how do we solve these two problems here. The first one, if we look at the right side, actually it's very easy to tell something here, right? So we have this term a prime, b and b, and we have this term d, right? So maybe first let's try to define a new variable to replace the common part. So if we set x equal to that and take x back to the function, we get the function f actually equal to x or c and x, right? Then things getting easier. So basically we can use the distributive law to open the parentheses. So we get x and x or C and X. So this is 2-11, the distributive law. And X and X, we know it should equal to 1. Oh, sorry, not equal to 1, equal to X, or C and X. X and X equal to X. This is actually coming from 2-60. Finally, this actually is the absorption theorem. So the result is X. So this is the absorption theorem. And because X equal to that, so we need to write it back. So you can see this simplified expression only requires a NOT gate, an AND gate, and an OR gate, 3 gates. We realize the function. But if you use original expression, you can tell how many more gates you need to use. Okay, so that's why we do the simplification. Now let's check the second problem. Similarly, we can find some common terms here, right? So D or EF is common. Actually, the other part, A or B prime minus C, is also common. So this time, let's set X equal to A or B prime C, and the Y equal to D or EF. Let's see what we can get. So Z equal to X or Y, and X or Y prime. So what is this? This is actually the uniting theorem, and the result is equal to X. You can check the expression 2-15D. That's a uniting, the dual form of uniting theorem. And X equal to A or B prime C. Okay, so you need practice a little bit more to learn how to use those theorems. But basically, it's not that hard. Okay, guys, that's the video for today. If you think my video is helpful, please help like, share, and subscribe. See you next time.